The second question gets a lot trickier from the very first part. You can see again it's a question 6, but 7 marks part 1, 5 marks part 2. So as I said, a lot trickier at the start. We have got P being rotated around this fixed vertical axis. Particle P is of mass 0.5 kilograms. There are 2 strings, equal length. Both strings are taut, each is inclined at 6 degrees to the vertical. Constant speed of 3 meters per second, and we know that the radius is equal to 4. So just before I forget, I'm going to write those 2 things on there, and why not the mass of P as well. So calculate the tension in the 2 strings. There are 2 different strings, so we need to call them 2 different things. So we can't, assume they're the same. So I'm going to call this T1 there, T2 there. Of course, we need to consider all forces acting on P. So we also have the weight, 0.5 g. I want to mark on the angles as well. This is all getting a little bit busy already, so what I'm going to do, and of course it's always good practice, draw a diagram. I have got my weight acting downwards, 0.5 g. There is my horizontal, and that of course is where my acceleration is acting. T1, T2. I need to mark on some angles. Now, if I marked on the 60 degrees there, which of course it is, I've got, Z angles, so 60 degrees going on in there. It would just mean additional lines making that diagram just a little bit more busy. So I'm going to mark on those 2 angles there, being 30 degrees. Okay, 2 different directions, vertical, horizontal. It's always easier to deal with the vertical first if you can, because of course it's in equilibrium. If it's in equilibrium, I know that forces up equal forces down. So forces up, well, I've got that vertical component of my tension force. So my tension force here, it is opposite the angle, so that is the sine component. So I'm going to have T1, sorry, I didn't mark on, T1, T2. I'm going to have T1 sine 30. That's the only force going up. Going down, of course, I've got, again, it's going to be the sine component because it's opposite the angle. I've got the sine component of T2. The weight is also acting downwards. So I've got that additional 0.5 g there. But I don't need to use F equals ma, forces up equal forces down. And let's just, while we're here, sine 30 is equal to 0.5. So very nicely, we've got 0.5 T1, a 0.5 T2, and a 0.5 G. 0.5s all go. So I've got T1 plus T2, sorry, T1 equals T2 plus G. 1 equation, 2 unknowns. So we know the drill. What is going to happen is that we are going to have a second equation by considering what's going on horizontally. Really, I guess I should have put my arrow going the other way because that's where my acceleration is going. So I am going to be using F equals ma, but considering that direction being the positive direction. So going in this direction, I've got both components, both horizontal components of my tensions. It's going to be the opposite component to what we had up here. So T1 cos, because it's adjacent. The tension component from T2, of course, is acting in the same direction. So that's why I have got both of them being plus. There is nothing, of course, opposing the motion, nothing going in this direction. So that is equal to the mass, 0.5 times by the acceleration, and we're told a speed, so we're told v, so I'm going to use v squared over r. Cos 30, root 3 over 2 t1, root 3 over 2 t2, and that is 0.5 times by v squared, 3 squared over 0.4. So 5 over 4, that will be 545 over 4. So I have got 3 over 2 t1 plus 3 over 2, so root 3 over 2 t2 is equal to 45 over 4. I've got two equations, of course, one equation there, a second equation there, simultaneous equations. I will just, of course, have to rewrite that. T1 minus, sorry, a big minus, T2 is equal to G. So I'm going to be using that equation together with that equation. Go straight into a calculator. Don't, faff about with solving it using pencil and paper. I've already typed those coefficients in, and that isn't the correct answer. So root 3 over 2, root 3 over 2 plus is equal to r. I've got 45. I need to change that to 45 over 4. And then I've got 1, negative 1, 9.8. So hopefully, yes, that's a little bit like it. You can see the first one, T1 is equal to 11.4. T2 is equal to 1.60. Those, of course, are both newtons. Okay, so part 2. The particle now moves with constant angular speed omega, and the string BP is on the point of becoming slack. So BP meaning this one here. Okay, now you get quite a few questions like this. Something's on the point of becoming slack, or it's on the point of leaving the surface. So what it's saying is that that is just about to be 0. So of course what we do for the aid of the calculation, we assume that it is equal to 0 because we are just before that point. So we now know for this point, I'm going to just turn or get a new sheet of paper for this so we can see. So the key part then is that the tension in BP, T2 is equal to 0. So that means that we've only got my T1 force. I've still got that same angle of 30 degrees. And I've got 0.5 G. Still go through exactly the same processes. We are looking to see what's going on in the vertical direction. So I can use what I had before, but this time I've just got the T1 component. That is equal to 0.5 G. And very nicely here, that goes. So T1 is equal to G, which is 9.8. In that direction, we're using F equals ma, but this time with omega squared r. F, it is still the cosine component, so I've got T1 cos theta, and that is equal to m 0.5 omega squared times by r. The radius is still 0.4. So I think really this question is just testing that you know about the second form of the acceleration, because everything else is exactly the same. 0.5 times by 0.4 omega squared. Omega squared then 9.8 times by root 3 over 2 divided by those two things, which is 0.2. Working out that, we get 42.4. So omega is the square root of 42.4, 6.51 radians per second.